Hello, welcome to the course in Emerging Domain Electronics Engineering. This is lecture 20. So, in the last lecture we have seen the subtraction and addition using ones and twos complement. After that, in this lecture we will see the logic gates. So, first of all, what are logic gates? So, logic gates are the basic building blocks of any digital system. So, it is an electronic circuit having one or more than one input but only one output. The relationship between the input and output is based on some logic, on some certain logic. So based on this logic, the gates are named as AND gate, OR gate, NOT gate. We will see further. NAND gate is also there, NOR gate is also there, XOR and XNOR. So these gates are used in the digital circuits or digital systems to implement the applications in digital systems. Are we can implement a combinational circuit, we can implement a sequential circuit. So we will be using these. So we have the types of logic gates. So how we can categorize these logic gates? So on the basis of we can say we have the basic logic gates. Under this head we have the AND gate, OR gate and NOT gate. After that we have the universal logic gate. So we will see what is the definition for universal logic gate, but at this particular moment we can say that if we can build any other logic gate using these gates, then we can say it is a universal logic gate. After that, some other logic gates are also available with us, which is XOR gate and XNOR gate. So first of all, we'll start with the basic gates. So in basic gate we have the NOT gate, which is the inverter also. So NOT gate, the representation for this NOT gate is this triangle with a bubble. So if we are providing A as the input, then we have output Y. Y equals to A bar, means A complement, or Y equal to A dash. Both the representations are same. Both the representations shows that the output is having a complement relationship, Y equals to A bar, something like this. Means how we can see this NOT gate as, if we are providing some low voltage, then then this output will be the inverted. Means if we are providing low, then automatically the output will be high, and if we are providing high voltage, then automatically the output will be low. This is the inverter. So if we will represent this high and low voltage by 1 and 0 in binary, then what we can say over here is that if 0 represents low, then output is 1, which is high, inverted, and if 1 is high, then output definitely is low, that is the inverter. The IC, this NOT gate now is not available in a discrete form. So this NOT gate is basically available in a IC form, in a package form. So this IC, integrated circuit, IC number is 7404. So this 7404 is basically a 14-pin IC, 14-pin DIP packaging. We will see what is this DIP, dual inline packaging, we will see. So 14 pin, out of these 14 pin, pin number 7 is ground and pin number 14 is VCC, which is plus 5 volt. After that, the remaining pins, if we'll see that pin number 1 is input, pin number 2 is output. Similarly, pin number 3 is input, pin number 4 is output. So in this particular IC, what we can say, we have 6 NOT gate. We have 6 NOT gates. So if we are providing a pulse, let's say at pin number 1, which is something of this type, 0 1 0 1 0 1 0 1, then the output which will be visible at pin number 2 at this particular pin will be 1 0 1 0 1 0 and so on. So this same, the inverted waveform will be definitely visible at pin number 2. So this is in theory basically, but in practice this waveform is bit delayed. In practical systems, this waveform is bit delayed due to the propagation delay. Propagation delay or the propagation gate delay is basically the delay provided by the gate. Means if it provides input signal, then output will be available after some time. That this is not a very big time, that will be very small time, but output is bit shifted. After that we have the AND gate. So AND operation, y equal to A and B. The symbolic representation for AND gate is this one. So y equal to AB, which is equal to BA also, and this law is known as the commutative law. We will see in Boolean what are the laws. So commutative law, A dot B is equal to B dot A, and this IC number for AND gate is 7408. Again this IC 7408 is a 14 pin IC, out of which pin number 7 and pin number 14 is basically ground and VCC respectively, and the remaining pins are corresponding to input and output. Let's say we will see this particular gate 1. So we'll have pin number 1 and 2 as input and pin number 3 as output. So in this particular 7408 IC we have 4 AND gates, and we can see the waveform also. Now first of all we will see the truth table for, let's say, 3 input AND gate. This is 3 input AND gate A, B, C. So the output will be y equals to A dot B dot C, which can be represented at A dot B dot C, or we can say A dot B dot operation with C. So this is nothing but the associative law. So both the laws are verified, means the commutative law as well as associative law is verified for AND gate. This truth table, how this truth table will come? These are the inputs and y is the output. So we can observe that if any of the input is 0, then the result is 0. If all the inputs of an AND gate is 1, then the output is 1, like this. So if we are providing the pulse at pin number 1 and pin number 2, then at pin number 3 we can observe the result like this. But again in practice this result will be little bit shifted due to the propagation delay of the logic gate. The third gate, which is OR gate. Now in OR gate, this is a symbolic representation for OR gate, and y equals to A plus B, which is equal to B plus A. So this is known as a commutative law, what we have seen for AND gate. Similarly, if we have the 3 input OR gate, then y equal to A plus B plus C. So we can perform first B plus C and after OR operation with A, or we can say A plus B and after that OR operation with C. That is the associative law. So again for this OR gate, the associative law and the commutative laws are followed. Now the IC number is 7432, which is again a 14 pin IC, out of which 2 pins are for ground and VCC, and the remaining 12 pins are corresponding to input and output. So again for the 7432 IC, we can say we have 4 OR gates, because again this OR gate will not be available in a discrete manner. It is available in a IC form, integrated circuit form. So this is the representation of input at pin number 1 and pin number 2, and we can visualize this particular waveform at pin number 3. Now we have this truth table. So what we can say, if any of the input is 1, then output is definitely 1. If any of the input is 1, then output is definitely 1. So we can say that for the enable of OR gate is basically 0, and the enable for AND gate is 1, because if we are providing 1 at any of the input, then output will definitely be 1, means it is irrespective of the second input, means the second input can take any value but the output will be fixed to 1. That means the gate is disabled, the gate is not working properly. So after this we have the definition for logic gates. As we have seen that logic gates, universal logic gate is a gate which can implement any Boolean function without the use of any other type of gate. So we have the NAND and NOR gates as a universal gate. So in practice these gates are having some advantages, that it is economical to use, easy to fabricate, and are definitely used in the IC digital logic families. There are various logic families like TTL, ECL, transistor logic, emitter coupled logic, ECL, Schottky TTL. There are so many logic families. So we can have means using NAND and NOR gate we have these logic families. So for these universal logic gates, first we'll start with NAND gate. So NAND gate is basically AND followed by NOT. So what is the output at this particular end? A dot B, and here it will be A dot B bar in the inverter. We will see what is the De Morgan's law in Boolean, but here we can say that this is equivalent to A bar and this dot is basically converted to OR B bar, something like this. And this is a symbolic representation. This is a symbolic representation for NAND gate. Now we have the truth table. So 0 0, when both the inputs are 0 we have 1, like this. Means if both the inputs are 1 then only the output is 0, otherwise at all the time the output will be 1. And since it is a universal logic gate, the IC number is 7400, again which is a 14 pin IC. So in this 14 pin IC we have 4 NAND gate. 4 NAND gates. So we can represent this in the OR form, something like this, that if we are providing 2 inverted input A bar, 2 inverted input means A bar and B bar, and we are just using this OR gate, so the result is quite same, y equal to A bar plus B bar. That is a commutative law. After this we have the second universal gate, which is a NOR gate. So the NOR gate is something you called as the OR gate followed by a NOT gate. We have a OR gate followed by a NOT. So at this particular moment we have A plus B, and here we have A plus B bar, which is same as A bar dot B bar. We will see with the help of De Morgan's law in the Boolean algebra. So the output is y equals to A bar dot B bar. So again the IC number for this NOR gate is 7402, which is again a 14 pin IC having let's say 4 NOR gate. But we can say here that previously for all the gates we have 1 and 2 was the input and 3 was the output, but here we have 2 and 3 as the input and 1 as the output. Similarly 5, 6 as the input and 4 as the output. So the output will be visible at pin number 1, pin number 4, pin number 10 and pin number 13. So if you want to represent this with the help of AND gate, so what we have 2 inputs A and B with NOT gates over here, and if we are using a AND gate, then we can have y equals to A bar dot B bar, something like this, again which is a commutative, Now we have the XOR gate. So other type of gate we have XOR and XNOR. So this is a symbolic representation or, and we have something like this. The representation, the logic representation, we can see with the help of truth table that if both the inputs are 0, then the out means when both the inputs are same, then the output is 0. If any of the input is different, then output is definitely 1. Then output will be definitely 1. So we have the Boolean representation is y equal to a XOR. This is a symbolic representation for XOR. So if we'll expand this, this is referred as y equals to a bar b plus ab bar. A bar b plus ab bar, and the IC number for XOR is 7486, which is again a 14-pin IC. So correspondingly we have 4 XOR gates. We have 4 XOR gates. Something like this. 1 and 2 are the input, and naturally 3 is the output. So this is the truth table, the symbolic representation, and the IC number for XOR gate. So it must be remembered that when both the inputs are same, the output is 0, and when both the inputs are different, then the output is different. Now for XNOR. What is XNOR? XOR followed by a NOT gate. So XOR followed by a NOT gate means it is represented by something like this. This is a symbol for XNOR. So in Boolean form it will be y equals to a bar b bar plus ab. So a bar b bar plus ab. So we have the truth table over here. Now here we can see that if both the inputs are same, then the output is 1. Similarly, when both the inputs are different, so output is 0. Output is 0. Means the output is in opposite form as that of a XOR gate. Means XOR followed by a NOT gate is equivalent to XNOR. The IC number is 74266, which is again a 14-pin IC. 14-pin IC having 4 XNOR gate. So these are the basic gates, universal gates, and other type of gates. So after this we will see that what is the universality of the NAND gate. Means what we have said that we can build any logic gate with the help of NAND and NOR, that is the universality. So we will see how we can realize the NOT gate, AND gate, OR, XOR and XNOR. So first of all we have the symbol for NAND gate. Now first of all we have the NOT gate. NOT means if both the inputs are connected to the same input A, then the output will be A bar, which is the function of an inverter. Inverter is nothing but a NOT gate. After that, if we have this NAND gate, and again we will put inverter over here, then we will be obtaining a result A dot B. So A dot B, this logic representation is corresponding to AND gate. So for AND gate, how many NAND gates are required? The answer is 2 logic gates are required. After that, for OR gate, if you are providing 2 inverted inputs A bar B bar, and if we will use the NAND gate again, so this is 1, this is 2, this is 3. So we can see that we will obtain A plus B. A plus B, the logic representation is corresponding to OR gates. So for OR gate we required 3 number of NAND gates. After that OR gates, after that we have XOR and XNOR. So for XOR we required 1, 2, 3, 4. This is NOR. This is NOR basically, and this is XOR. 1, 2, 3, 4. So the output is A XOR B. Similarly, after XOR we have XNOR, then the output is equals to A XNOR B, something like this. So we required here 5 number of NAND gates. So we have basically built all the other gates with the help of NAND gate. That is called the universality. Next, with the NOR gates, now it's bit different. First we'll have the symbol of NOR gate. So we have first the inverter, means again to implement an inverter we required either one NAND gate or one NOR gate. After that, to implement OR gate we required 2. To represent AND gate we required 3 NOR gates. After that, if we'll say XOR and XNOR, so for XOR we have 5, we can say over here like this. Here we need only 4. This is what is A is the input and XNOR, and this is A XOR B. So if we'll build a small table that how many gates are required, how many NAND and NOR gates are required to implement the other gates, then we can say that for NOT gate the number of NAND and NOR are equal. For AND gate, using NAND we required only 2, but with NOR gate we required 3. Similarly, for OR gate, XOR and XNOR we required 3, 4, 5. Similarly, for NOR gate we required 2, 5, 4, something like this. So I think this is quite easy how we can remember. Here we can see directly 1, 2, 3, 4, 5. Here we can say 1, 2, after that 3, after that 4 and 5, something like this. So after this we have the bubble pushing, means using this particular method we can represent any logic gate, means any circuit having AND gate, OR gate or any other Boolean function using NAND and NOR, using this particular logic. So bubble pushing is a technique to apply De Morgan's theorem directly to the logic diagram. So changing the logic gate AND to OR and OR to AND. After that, add bubble to the input and the output where there was none and remove the original bubble. So we can use this technique to convert means a logic into a NAND or NOR logic. So logic gate can be de-Morganized so that the bubble appears on the input or the output in order to satisfy the signal conditions rather than the specific logic function. So any active low signal should be connected to a bubble on the input of a logic gate. So if we'll see that what is this bubble pushing, we can say that if we will have here what is the output A dot B. So if we are providing bubble at the input and the output, this is the equivalent, means AND gate is equivalent to OR with the inverted input and the inverted output. Similarly, this OR gate, this is equivalent to the inverted input and the inverted output of a AND gate. Similarly, if we have this one inverted input, that is equivalent to one inverted input of AND and the inverted out. Similarly, these two techniques are also available with us. So these are very helpful if we want to implement a function using NAND or NOR gates. So we have this first example, that write a Boolean function for the output Q in terms of input A and B. So we have two circuits. So how we can proceed? We can proceed from left to right. something like this. So first gate we have the NAND gate, this we have the NOR gate, and this we have the OR gate. So by step manner we will write down what is the output. At this particular end we have A bar plus B bar, A bar plus B bar. Similarly we have over here A bar dot B bar, which is the output of NOR gate. After that we'll perform this OR operation, so the output will be A bar plus B bar plus A bar dot like this. This is the output. Here we are not minimizing this function, we can further minimize this using the help of Boolean algebra. The equivalent will be, we'll take A bar common, here we'll take B bar common. So with the help of the properties of Boolean function, this is equivalent to A bar plus B bar. We will see in our next lecture that what is the Boolean algebra. Now we have the second circuit. We have one AND gate, two NOT gates are available with us, again one AND gate and one NOR gate. So what is the output? Clearly at this particular input the output of first gate is A dot B. After that here we have A bar dot B bar, something like this. Then we need to perform the NOR operation. So if we are not remembering, then we can write down something like this: A dot B plus something A bar dot B bar, and with the whole bar. So clearly this particular relationship A dot B plus A bar dot B bar, which is equivalent to, if we'll write A XNOR B whole bar, which is equivalent to A XOR B, which is equivalent to A XOR B. So this is the output for this particular circuit. After that we have the implement the Boolean function with the help of logic gates. So here we are not minimizing, we just have a small question over here that how we can represent this with the help of gate. So if it is mentioned that you have only two input gates are available, then you have to use two input gates. Otherwise if you have multiple input gates, means if we have three input gates, then we have one AND gate for this one, second AND gate and third AND gate. After that, to perform this operation we need one OR gate, and after that we have C bar and A bar. So to implement this C bar and A bar, again we need the inverter, something like this. So we can use, instead of two inverters, we can use one inverter. We can provide the same input to both the pins. Here we have A bar, something like this. Here we have C bar. So ABC, something like this. ABC bar is the output of this. A bar B C bar is the output for the third logic combination, and the overall is provided by the OR gate. So this is the implementation of the Boolean function. Now we have the next question, that implement the Boolean function z equal to AB plus CD using the NAND gate. So how we can perform? First of all, we will perform this using the basic gates. AB, one AND gate, CD, again one AND gate, and one OR gate. Now if we will provide a bubble at the output of this pin, and just to compensate that, we are providing a bubble at the input of OR gate. So this is first AND gate, this is second AND gate, and naturally this is equivalent to a NAND gate. So as a whole, how many NAND gates are required? Three NAND gates are required. So in this way we'll use this bubble pushing technique to convert a Boolean function into its logic representation in the form of NAND gate and the NOR gates. So these are the references. Thank you.